Okay, do you have any questions? No? Okay, so last time I asked you to think about this question, so go ahead and do so. Try to see if you can argue whether this function is surjective or not. Let me take attendance while you do this. Otherwise, I will just forget. Daniela Áviles, Andy Brito, Raúl Campos, Brian Cruz, Miguel Díaz, Brian Echevarría, Anthony Fuentes,
Here.
Ian German, Talia González, Carlos González, Sebastián González, Alejandro Escaray, Alfredo Llanes, Edwin Mendieta, Mario Núñez, Leonardo Quevedo, Michael Valdez. Attendance out of the way. All right, so I asked you last time to think about this question. So I gave you this function, and then the question is this function surjective? So notice that here what this function does is it takes a pair of integers, and then the output is difference of their squares. Okay. So when a question like this is presented to you, first of all, you should try to see if you can understand the formula and develop some sort of feeling where the answer should be true or not. Okay? Because depending on what your feeling is what you then try to set out and argue. For example, if you think that this really should be true, then you try to prove it. Okay? But if this is false, you can try to prove it, you're gonna fail. So if your feeling tells you, oh, this doesn't seem to work, then you invest your time in looking for a counterexample. Okay? So it's good to have an initial sort of feeling of whether this could be true or not, because that's gonna guide you. That's gonna guide your process to get quicker to the answer. Okay? If you don't have any feeling, then the price that you pay is that you just have to start trying one choice and then hopefully realize that that choice doesn't work and then it's the other and so on. Anyways, one way to develop a feeling here is to try to say this in common language. What's happening? What is this function doing? So this function is sending a pair of numbers to their difference, the difference of their squares, right? And to us, that this function is surjective, is equivalent to say what? Surjective means that every element in the codomain, so every integer has a pre-image, right? In other words, that for every integer, you can find a pair of numbers, a pair of integers, so that when you subtract the squares, you get that given integer. In other words, saying that this is surjective is to say that every integer can be written as a difference of two squares. That's really what the question is about. This is, you need to say yes or no to the answer to the question, can every integer be written as a difference of two squares? For example, 5, you can write it as 9 minus 4. 9 is 3 squared, and 4 is 2 squared. Okay? So 5 can be written as a difference of two squares. So 5 satisfies that property. Now the question is, does every integer satisfy this property? That's what we want to answer. So what do you think? I mean, we will then explore, but what do you think? What does your feeling tell you? Do you think this is true all the time, or there could be a case in which it doesn't happen? What do you think? Do you understand the question? No. So again, this basically means, so being surjective means that the entire codomain is covered by the function. In other words, every integer comes from a pair of numbers like this. In other words, every integer can be written in this form as a difference of two perfect squares. That's what being surjective means in this particular case. So my question to you is, do you think this is a reasonable claim? Yeah. Do you think every integer can definitely be written as a difference of two perfect squares? I already gave you an example, like 5 we can do it, okay? 5 we can do it. So how about in general? What do you think? Notice that being a difference of perfect square, the numbers you have to have like a special structure. There are infinitely many numbers out there. So to just blindly claim that this will always work is a little bit stretching it too far. Okay? So what I would do is, I would think that this is too much restrictive for every single integer to satisfy this property. So what I would try to do is try to see if I can come up with a counterexample. Okay? If you try and you cannot get a counterexample, then okay, maybe you need to stop and think that probably this works, and then you go ahead and try to prove it. Okay? But I will invest my energy first in trying to disprove this, to show that this is not surjective. Because this is telling me that integers, they have to be very special, difference of two squares. Okay? And I don't know, doesn't really come to my mind that this could be true. And in fact, we're going to argue otherwise. Okay? Now, if I'm going to look for a counterexample, make sure that you work with small numbers first. Okay? For example, don't use 5 because 5 has a preimage. Okay? What's the preimage of 5? What is it? Okay, what goes in here? But what's the preimage? The preimage is the pair of numbers that you need to plug in to get 5. What pair of numbers do you plug in to get 5? 3 and 2. So the preimage is 3,2, right? So don't pick 5. If you're looking for a counterexample, pick something else. Okay? So let me do it here. So our first example is determine whether the function f from c equals z to c given by f of m comma n equals m squared minus n squared is surjective or not. And then whatever we say, we're gonna justify. Okay? So solution. For example, just to understand a little bit more the function, so know that 5 is equal to f of 3,2 because that's 3 squared minus 2 squared, which is 9 minus 4. Okay? So, for example, 5 can be written like that. But to say that every single integer can be written as a difference of two perfect squares is taking it a little bit too far. And I'm going to start with the simplest one. First of all, don't pick a perfect square. If you pick a perfect square as your integer, it's going to work. Because you can always pick m to be your integer and n to be 0. Right? Like if you pick 25, yes, okay, I pick m equals 5 and n equals 0. That's going to work. Okay? So don't pick perfect squares either. So I'm going to pick 2. So I'm not going to pick 1, I'm going to pick 2. And the moment that I tell you 2, hopefully you start thinking, can you really come up with two perfect squares whose difference is 2? You can start thinking a little bit, and you're not going to find them, okay? Now, let's prove that there are not perfect squares out there whose difference gives you 2, because maybe not for small numbers, but maybe for very, very, very big numbers in the millions, there could be a pair whose difference is 2, okay? And it happens that those two are perfect squares. So we need to produce some sort of argument, okay? So claim 2 has no preimage. Okay? In other words, what I'm saying here is that there are no m and n integers such that f of m comma n equals 2. That's my claim. Okay? So how are we going to prove it? Well, we're going to do it by contradiction. Okay? Let's assume that we can find a preimage for 2. Let's assume that we can write 2 as a difference of two perfect squares, and let's show that this is impossible. Okay? So proof by contradiction. Again, I'm picking 2, but you can pick, something else. But 2, we see, is pretty easy to prove. So by contradiction. So assume, the opposite of what we want. So let's assume that there are two integers, m and n, such that f of m comma n is equal to 2. Okay, so let's suppose that 2 has a pre-image, but there is a pair of numbers, so when you plug in into the function, then they give you 2. Do you understand this so far? All right, now what does this mean? So then this means that 2 can be written as m squared minus n squared. Yes? But now this is a difference of squares, so we can factor this. How do we factor this? This is n plus n times n minus n. Now I ask you, so this product is equal to 2, right? So what can you say about each of these parentheses? If a product of two numbers equals 2, what can you say about these numbers? Say that again?
They're even. One of them is 2.
There are very few choices here. One of them has to be 2 and the other one has to be 1. Or maybe -2 and -1. Right? I mean, there is no other two numbers that you integers, okay? We're not dealing with fractions here, integers. There are not any two integers that you can multiply and get 2 other than 2 and 1 or the negative version, -2 and -1. Do you understand this? Plus or minus 2 with plus or minus 1. Because 2 is prime. That's it. You cannot split it any other way, okay? So let's just argue that in any of those cases, it's impossible for this product to happen. If we can do that, then we're good to go. So then there are really 4 cases, okay? And there are 4 cases. So case number 1, n plus n is 2, and then n minus n is 1, okay? Case number 2, the other way around, n plus n is 1, and then the one that is equal to 2 is the other factor. And then case 3 and 4 is the same thing as this one, but with the negative version, -2, -1, okay? Flipping those. Now, I'm gonna say, 3 and 4 are similar to 1 and 2, but with -1, -2 instead. Okay, I'm gonna leave it to you. We're gonna prove 1 and 2, that 1 and 2 leads to contradiction, and then I'll leave it to you to check that in a similar way. 3 and 4 will lead to a similar contradiction, okay, because they are essentially the same thing you're about to see. Okay, so if we assume that 2 has a pre-image, it means that 2 can be factored. That's basically what we're saying. We can factor 2 in this form, and that means then that the factors, they have to be 2 and 1, or the negative version of those. But moreover, this is telling me that 2 is equal to the sum of these 2 integers, and 1 is equal to the difference of these 2 integers. And this is where we're going to get a contradiction. For example, from here, what follows? So let me say here. So in case number 1, since m minus n is equal to 1, then, for example, we can say that m is n plus 1. Yes? So that means that we can, the number 2, we can write as m plus n, right? That's this. And now I plug in my m. So that's 2m plus 1. So we're saying that 2 is equal to 2m plus 1. So what is n? So that means 2 equals 2m plus 1. So that means n is 1/2. What's the problem here? It's not an integer. And we say m and n are integers. You see? M and n are integers. And if we are in this case, it leads to the only thing that this can happen is if n is equal to 1/2. That's impossible. It cannot happen. Do you understand this? That's a contradiction. So this right here is a contradiction. Since n is an integer, so it cannot be 1/2. Okay. All right. So case number 1 is impossible. Oh, well, maybe it's the other way around, right? Maybe this is the one that's equal to 1 and this one is 2. Okay? But we're gonna play the same game. The second case, then we have that n plus n is equal to 1. That means that n is 1 minus m. Okay? So 2 equals m minus n, which is m minus 1 minus m, which is m minus 1 plus m. So that's 2m minus 1. So we have that 2 is equal to 2m minus 1. So that means that, subtract 1. So 1 is equal to 2m, which means that m, once again, is 1/2. Again, impossible. M is supposed to be an integer, right? So this is also a contradiction. Since m is an integer. So case number 1, case number 2 are impossible to happen. And then in a very similar way, you can prove that 3 and 4 are impossible, because again, the only difference is that you have a -1 and a -2. But you play the same game. So for the one that has a -1, solve for one variable, plug into the other one, and then you're gonna get that cannot be an integer, so it's not gonna work. Okay? So for example, let me just show you number 3 quickly. So number 3 will be, let's say m plus n is -2 and m minus n is -1. That would be the possibility. Well, from here you get that m is n minus 1. So -2 is m plus n, which is m minus 1 plus n. That's 2m minus 1. And now you solve, right? So -2 equals 2m minus 1. So then 2n equals -1. So n is -1/2. Again, contradiction. Okay? And then, similarly for number 4. Similarly, 4 leads to a contradiction. So to recap, we started by saying that 2, assuming that 2 has a pre-image, okay, meaning that you can write 2 as a difference of 2 squares, and then after that, then that means that there are 4 cases that can happen, because that means you can factor 2, and so the factors are either 2 or 1, or -2, -1. That's all, plus or minus 1, plus or minus 2. And we show that in any possible configuration, it doesn't work. So the conclusion is that 2 cannot be written as a difference of 2 squares, therefore 2 has no pre-image, therefore our function is not onto, is not surjective. Because there is an integer that doesn't have a pre-image. There's no arrow going to 2, if you think about the arrow diagram. Okay? So therefore 2 has no pre-image. Okay? Hence F is not surjective. Okay, questions? Yes.
The second case, on the line it says 2 equals 2m minus 1. How do you
Sorry. Yeah, you add 1, so it's a 3. Okay, good. 3/2, again, contradiction. Good catch. All right. Any questions? Did you understand this? Again, of course, to be able to understand what we're doing here, you need to know what onto means. Do you understand what surjective is? Means every element in the codomain has a pre-image. So every integer comes from a pair of integers, in C cross C, so that when you apply the function, you get that integer. Okay? And we just argue that 2 doesn't come from a pair of numbers under this rule. Okay? So it cannot be surjective. All right, so that was that one. Okay, so that was that question. Let's see, let's do a couple more just to have more practice. So number 2, prove. let's do something easy now. So prove that the function f from R to R given by f of x equals x plus 5 is onto. Okay. In fact, let's exploit this. Let's prove that this is a bijection. So what does it mean to be a bijection? It means that it's both one-to-one and onto. Okay, injective and surjective. So to prove that this is a bijection, we have to prove two things. So first, we need to prove injective or one-to-one, whatever you decide to use, the same thing. And then second, we need to argue that it is surjective. Remember, surjective means onto, injective means one-to-one. Okay? All right, so I'm gonna write down the definition here so you can have it fresh. But the idea is you need to know this definition so you can properly prove these things. So what does injective means? What's injective in the context of this problem? It means that for every x1, okay, so the domain is, okay, so that's for every x1 and for every x2 in R, we have that if x1 is different than x2, then f of x1 is different than f of x2. However, when you are given the function with a formula like this, it's easier to work with the contrapositive version of this, okay? Which is equivalent to it. So I'm gonna write the contrapositive directly. So f of x1 equals f of x2 implies that x1 is equal to x2, okay? So when you're presented a problem in which the formula is given to you, this is the way to go, okay? Because the other one is a little bit more strange to work with. If you use the original one, which is x1 different than x2 implies f of x1 different than f of x2. This one is easy. Okay, so basically we need to argue that if given two inputs, if they produce the same image, then that means the inputs were the same to begin with. In other words, it's translated to saying that different inputs have different outputs, which is a one-to-one. Okay, so how do we prove something like this? First of all, we need to let x1, x2 be arbitrary numbers, right? Because we want to show that this is a universal statement for all. But then we want to make sure that this implication is satisfied. Understand that when this part is false, this is automatically true, right? So we don't have to worry about this being false. And that's the proof technique of implication. How do you prove that an implication is true? You assume P, and then you prove Q, right? So let x1, x2 be arbitrary real numbers such that this happens. You want to assume that this happens, and then your job is to argue that this is going to happen. Okay? The second part. So that's how we begin. So let x1, x2 be real numbers such that f of x1 is equal to f of x2. Okay? So we take a pair of numbers that gave us the same output. Our job now is to show that the inputs actually were the same to begin with. Okay? So the reason why this is very easy to work with when the formula is given, because now all you have to do is put the formula and do algebra. Okay? So we have f of x1 is equal to f of x2. Then what does this mean? Plugging into the function. This means x1 plus 5 equals x2 plus 5. Subtracting 5 from both sides leads to x1 equal x2, which is what we want, right? So if the two inputs have the same image, then the inputs are the same. We just prove that, okay? So it's just a little algebra. So f is injective. Did you understand this? Again, when the formula is given to you, this is the way to go because you just do algebra, okay? You set it up. You have your equality of the outputs, put your formulas, and then start simplifying and solving. Okay. And of course, if you cannot get to this line, then that means maybe it's not, and then you have to look for a counterexample. Okay. Like for example, if you think about the x squared function and you try to do this blindly, then you may be tempted to start taking square roots, but you have to be very careful. When you take square roots, remember you have two choices, the plus or minus. So to be more careful, you should do this factor and then you see that there are two solutions now. X1 equals negative x2 or x1 equal x2. So yes, it's true that if they are equal, that will work, but also notice that there is another possibility, and that's the problem, right? That's why x squared is not one-to-one function. Now, if you restrict the domain from the positive reals to the real numbers, that means that this condition is impossible unless they are both zero. So if you can neglect this somehow, then you're good. Okay, and it will be one-to-one. So just be careful when you're doing the algebra. You will get some tricky expressions. All right, the point is this function is injective, it's one-to-one. Remember, our job is to show there is a bijection, so we need to argue both. That is injective and that it is surjective. So to prove surjectivity, let's write down the definition. You need to know what you want to prove. So who can tell me the definition applied to this scenario? What's the statement for surjective?
F of A is equal to B. For all B in the set B, there exists an A.
Okay, but what's set B here in this problem?
R.
Okay, so if you don't mind, I'm gonna use X and Y.
That's right. Yeah.
So what should I use, Y or X?
X. Y.
And remember, we are in the output, so Y, right? I mean, you do whatever you want, but just do yourself a favor, and whoever's gonna read your work a favor, be consistent. You can use X, but you need to understand that now X is your output, not your input, right? So for every Y,
There exists an X.
there exists an X, where?
In R.
In R as well, yes?
Such that F of X equals Y.
Equals 1. Do you understand this? In other words, that for every number, for every real number, you can find another real number, so that when you plug it in, you get the one that you started with. Okay? So this is a universal statement. So how do you prove something like this? You need to start with an arbitrary element here, and then construct an element that satisfies this condition. Right? So you need to show that for any element in this set, you can construct or you can find such an element in this set, which happens to be the same in this case. Okay? So that this happens. So if you have been doing the homework, you will see that typically, when they are doing this, then they say, okay, let Y be arbitrary, and then they say consider X equals to this, and they give you a formula. Boom. So the question is, where is this formula coming from? Well, you want this to work, so you secretly, in a corner where nobody sees it, you write this down and you figure out what X has to be in terms of Y. Because the idea is that you're given Y, you start with Y, and you want to get X. So for X, in other words, I call this a corner computation. This is something that people don't see. You do it, and then you throw it away. And then you look clever. Oh, how did he come up with that formula? Well, he did this, okay? So what do we want? We want f of x to be equal to y, which means we want x plus 5 to be equal to y, right? Because it's a function, x plus 5. So 1 must be x, y minus 5, okay? So now you have your little formula. So now what do you do to actually write the problem? Well, the proof, let y be a real number. Now, let's put x to be y minus 5. Nobody can stop you from doing that. And then all you have to do is plug that into the function and verify that it equals to y, and you're done. Okay? So now that we have that in hand, we're going to use it. So now we begin by letting y be a real number. So let y be in the reals be arbitrary. So this is whatever you want, whatever real numbers you want. Okay? Then consider x to be y minus 5. Now you need to argue that x belongs to the set that we're claiming. So we want x to be a real number. So the question is, if I make x equal to this, is it a real number? Yes, of course, because y is real, you do minus 5 is a real number, right? So consider x to be this. This is also a real number, okay? And what happens when we do f of x? That's x plus 5, which is really y minus 5 plus 5, which is equal to y. As predicted, given a real number, we found another one. So when you plug it in, you get the y. So you're done. Therefore, f is surjective. Okay, and since f is both injective and surjective, it is a bijection. Hence, f is a bijection. Questions? Any questions? Again, it's just a matter of knowing the definition and understanding what this means. Okay? And you can just do it in a couple of lines. That's all. All right, so let's see. Let's do one more interesting. So number 3. F of x. So again, injective and surjective. Okay? So determine whether f is injective or not, injective or not, surjective or not. And therefore, then you can deduce whether it is a bijection or not. Okay, one of these fails, then it's not a bijection. Okay, and then let's use f of x. Let's see, I'm gonna put the formula. So I'm gonna say x. So the formula is x plus 1 over x plus 2. It's a rational function. Now I want you to tell me function notation. How should we write this down? In other words, what's the domain? What's your a? So what's the domain? I will tell you what the codomain is. Otherwise, the subjective question is pointless. So what's the codomain? What's the domain? Sorry, the codomain. I'm gonna call it R. Gonna be all of real numbers. How about domain? This is a college algebra question. What's the domain of this function? What is it? Are you sure?
Every number except -2.
Except -2, right? So it will be R minus the set containing 2, set difference, right? Sorry, -2. Notice that -2 is not a good value, right? You cannot plug in -2 in there. So this is not a function from R to R because this function is not defined at -2. Okay, that will make 0 down here. You understand this? So you have to take that out. Other than that, everything is fine. And the formula is x goes to x plus 1 over x plus 2. Let's see, what do you think? Is this injective? Is this surjective? You know college algebra, you know pre-calculus. This is a pre-calculus question right here. How can you answer this question? Then the point of this class is to formally do it, but you should be able to tell me yes or no to each of these questions. Remember, when you want to study a function, what is it that you want to do? Let's see, those of you that have studied calculus, why did you study calculus for? What's the main goal of calculus 1, let's say? What's the upshot at the end of calculus 1? What do you want to do? You want to graph any function that comes your way. You learn a bunch of techniques to be able to graph functions, right? Why do we really want to graph functions? Because the idea is that once you have a graph, you know everything about that function. In particular, you should be able to tell me whether it's surjective or not, whether it's injective or not. Okay? So, if you want to know these questions, well, that's the function, and this is a function that you know how to sketch. This is a rational function, right? Now, remember, this has asymptotes, vertical asymptote, horizontal asymptote, all of that business that you learned back in college algebra and again in pre-calc. Okay? So I'm just going to do it quickly. So, this is a rational function. We know it has a vertical asymptote at -2. That's a forbidden line, right? When it has a horizontal asymptote of 1, y equals 1, because the degrees are the same, right? It's a quotient of the ratio of the leading coefficients. So that means the behavior at infinity, it goes towards this line. And then let's just plot some points. For example, what's the y-intercept? When x is 0, the y-intercept is 1/2. Right here. And then when is this function equal to 0? So what's the x-intercept? A fraction is 0 when the top is 0. That happens at -1. And then knowing these points, then I already know, and then you can plot the point between -1, -2 to see and so on. But the point is that this would be the behavior on this part. Okay, and then you're going to get this behavior on the other. All right. Again, this is, you learned all this stuff before, okay? In college algebra, pre-calculus, and so on. All right, so these are functions. Let's see. To see graphically whether a function is injective or not, there is something called, what is it? Horizontal line test. You have the vertical line test to test whether something is a function or not. Now the horizontal line test tests whether something is injective or not. Why? Because when you draw a horizontal line, if the graph of the function, if the line crosses the function at 2 points, what are you saying? By drawing a horizontal line, you're fixing a y, right? So if it crosses at 2 points, what you're saying is there are 2 different x's that give you the same y. So it fails to be 1-to-1. Okay? So the horizontal line test says that if any horizontal line that you draw crosses the function in at most 1 point, then it is 1-to-1. Okay? If it crosses at 2 or more, it's now 1-to-1. If you look at this picture, this top half, first of all, these 2 parts don't overlap, yes? And the top half, no matter what horizontal line you draw, is just gonna cross it at once, because this is strictly increasing all the time, okay? And similarly here, this is strictly increasing all the time, so we only cross it at once. So this is 1-to-1, okay? We need to argue it, but at least we know that the answer is yes for the first one. How about surjective? Is this surjective? Why not? So what does surjective means? What's the meaning of surjective?
That every value in the codomain has a preimage.
Okay. So in the terms of the picture, what does that mean?
Every y value should have an x value.
Exactly. So what can you say? Does every y has an x?
No.
One. In fact, that's the only one that doesn't have an x. Yes. I mean, in this case, surjective is like the range question. College algebra, they give you special to ask you, what's a range? Right? Remember, range is the image, and when the image, surjective means that the image of the whole function, the range, equals the entire codomain. Here, the range is everything except 1. You're missing 1, right? This function there's no x that give you 1. The blue is never touching, it doesn't have a point where it equals 1. So this guy is in the codomain, but doesn't have a preimage. So when you're going to say, no, it's not surjective. Now, when you argue, you need to prove that 1 is the one that doesn't have a preimage. Because anybody else will have a preimage, right? Anything above 1 is taken care of by this part. Anything below 1 is taken care of by this other piece of the function. 1 is the one that's missing. Do you understand this? Okay, so yes, it is injective. No, it's not surjective. Now let's justify. Why is good to know beforehand? Because if the answer is yes, you need to provide a proof. But if the answer is no, you know that you need to look for a common example. Okay? So it's good to know whether the answer will be yes or no. So just by looking at this picture, it tells me f is injective. I'm gonna say here horizontal line test. Okay? Let me write the words. Horizontal line test. And f is not surjective. The reason is because 1 has no preimage. Okay? Now we're going to argue. We're going to formally say this. Okay, so prove a yes of each of these claims. So for the first one is F is injective. Again, I'm just gonna show that if the outputs are the same, then the inputs are the same, okay? So let x1 is 2 be real numbers different than 2, different than -2. Okay, such that f of x1 equals f of x2. Our goal is to prove that x1 equals x2. We're just gonna do algebra now. So what's f of x1? That's x1 plus 1 over x1 plus 2, and this is x2 plus 1 over x2 plus 2. And now the algebra is a little bit more interesting than the one before, but still. So cross multiply. And then distribute here, so that's x1, x2 plus 2x1 plus x2 plus 2. And then on the other side, we get x2, x1 plus 2x2 plus x1 plus 2. Now notice that this term, x1 is 2, cancel with this one over here. And then 2's cancel out as well. Okay, so we are left on the left with 2x1 plus x2 equals 2x2 plus x1. So what we can do is move this x1 over here and the x2 over there, right? So subtracting x1, we get 2x1 minus x1, that's x1. Subtracting x2, we get 2x2 minus x2, that's x2. So x1 equals x2, as desired, okay? So F is injective, or 1 to 1. Now for the second claim, F is not surjective, meaning that it's not onto. Then we're going to provide a counterexample. And the counterexample is that for y equals 2, there is no x such that f of x equals 2. So let's argue this. So indeed, now here, how do you do this? Well, assume by contradiction, right? So assume f of x is equal to 2 for some x, for some real number x in the domain. Then that means x plus 1 over x plus 2 is equal to 1. Did I put 2 above? 1. Remember, 1 is the one that has no pre-image. So right here you can see already that something is fishy. What's fishy here? The top, whatever it is, the top is always less than the bottom, right? The only way that equation is that a ratio is equal to 1 is if the top is equal to the bottom, right? So this is always actually less than 1. Now we're going to get a contradiction immediately, because then this means that x plus 1 equals x plus 2 by multiplying, right? Just move this guy and multiply. The x's cancel out, and we end up with the statement 1 equals 2, which is certainly false, right? So this is false, so that's a contradiction. So there's no way this can happen, okay? So f of x is different than 1 for all x, and hence f is not onto or surjective. It's not surjective. Right. Questions? Yeah, I'm doing this so you see more examples than the one provided to you in the videos and so on. So remember, use the videos and the book to complement, okay? It's just that we don't have an infinite amount of time for me to do tons of examples, okay? So we did some proof in which we proved that something was surjective. Here is an argument, something that's not surjective. Then we prove we show how to show that something is injective. To argue that something is not injective, you need to come up with 2 different inputs providing the same output. Okay, like if you think about x squared, just say, look, 1 and negative 1. They are different, but they give you the same output. Okay, that's it, not injective. All right, any questions? No? Okay, so let me see. I guess let me do one last problem, but this time let's do it more abstractly. So, theorem. This theorem is going to have two parts. Part 1, I will prove it. Part 2, I'm going to leave it to you as a homework. So, here is a claim. First of all, do you know what an increasing function is? I mean, you know, but do you know how to define it? Increasing means the graph is going up all the time, and decreasing means the graph is going down. Do you know how to write this down formally? So let me give you the definition. Let y equal f of x be a function. And let's say it's from R to R, okay? But it doesn't have to be from R to R. So just take any domain you want, but it has to be a domain in which comparison makes sense, okay? So let y equals f of x be a function, then number 1, f is increasing. This is increasing. By increasing, I mean strictly increasing, okay? Sometimes people like to enforce this word. But technically, strictly increasing is the same thing as increasing. If you want to allow for some time, strictly increasing means always going up. People like to say strictly because it could be a case that's going off, then stays flat, then goes up, stays flat. But in that case, we say it's non-decreasing. It never goes down. It means it either goes up or stays the same. Okay. But increasing means strictly increasing. Okay. So f is increasing if. So we want to say that the graph is always going up. Going up, it depends on you look at it. Remember, we look graph from left to right, right? Because you want to say something like this is increasing, but it's going up if you look at it from left to right. You look at it from right to left, it's going down, right? So when you read graph from left to right, how do you say that you're moving from left to right? You use the x-axis. That means x1 is going to be less than x2, okay? And then how do you say that you go up? That's the y-axis. So f of x1, the y1, is going to be less than y2, okay? So if you have a smaller input, that's going to produce a smaller output. That's what you want to say. Or the bigger the input, the bigger the output. That means the graph is going up, okay? So just have a picture like this in mind. And the idea is, if here I pick x1 and here I pick x2, here is f of x1 and up here is f of x2. Okay, so f is increasing if for any x1 less than x2, we have that f of x1 is less than f of x2. In other words, increasing functions, they respect inequalities. You see, if x1 is less than x2, when I apply the function, the inequality stays. It doesn't flip. Okay? Decreasing functions, they flip inequalities. Because decreasing means the bigger the input, the smaller the output. Right? That's what it means to go down. So, number 2, f is strictly decreasing, meaning the graph is going down, if for any x1 less than x2. You still say this because you want to go from left to right. It's probably the same as you go from left to right on the x-axis. Now I'm going to say we go down on the y-axis. So now f of x1 is actually larger than f of x2. So you see decreasing functions, they flip inequalities. That's why when you multiply by -1, the inequality changes. Because what's the function? Multiplying by -1 means that you're applying the function f of x equals -x. And what do you know about this function? This is increasing function, right? So that's why the inequality flips when you're solving an inequality and multiply by -1. Okay, so that's what it means to be increasing and decreasing. Now, the theorem is to prove that, the statement is that if you have an increasing function, then the function is 1-to-1. And similarly, a decreasing function is also 1-to-1. Okay? I'm going to prove increasing. I'm going to leave decreasing for you as a homework. So theorem, by the way, if a function is either always increasing or always decreasing, we say is monotonic. Okay? So let me say here. So number 3, or a function that is always increasing or always decreasing. You know, it was not an interval going up then going down, so or always decreasing is said to be monotonic. So we use this word, you know, as a collective term for both of these equations. That way now I can nicely write the theorem. So the theorem is a monotonic function is 1 to 1. Now to prove it, you need to do 2 cases, increasing and then decreasing, okay? So the theorem, a monotonic function is injective. Okay, and I mean the proof I'm gonna leave it to you. So proof homework because we don't have time, but it's actually pretty straightforward. Okay, because to show that a function is injective here, it's good to use the direct definition. What's the direct definition? X1 different than X2 implies f of X1 is different than f of X2, right? Well, you need to assume that you have 2 different inputs, right? So let's show that is decreasing. Assume that is increasing. Okay, let x1, x2 be inputs such that x1 is different than x2. In particular, one is less than the other, right? Let's say x1. Doesn't matter. If it's x2, you just switch the indices. Doesn't matter. So then, because they are different, one has to be less than the other. So you have this. But if you have this, because the function is increasing, you have this, right? But if f of x1 is less than f of x2, that means f of x1 is different than f of x2, right? It's one line, okay? It's just understanding that the definition of increasing immediately give you injectivity, and similarly definition of decreasing, okay? So try to write it down yourself in your own, you know, formally, and have practice in that. And if you have questions, you can ask me next time, and then we'll write it down, okay? So next time, I'm gonna start with cardinality. And we're going to keep on talking of function because we need this to talk about cardinality. So we're going to keep proving the stuff, our bijections and so on in the next section. Any questions? Okay, after cardinality, we're going to have our next exam. Okay, so make sure that you start preparing for it.